Hello everyone. So welcome to the first practical in electrical circuit theory paper. So the first practical that we are going to do today is verification of Thevenin's theorem. Um, I'm sure a lot of this theory of this particular theorem will be covered up in your paper while explaining. So what I'll do is I'll just briefly give you the only what is required for this particular theorem, the brief thing, and straight away we will do the practicals, the practical aspect of this Thevenin's theorem. Fine. So the aim of this theorem is to verify Thevenin's theorem for a given network. Okay, so you will be given a circuit, okay, containing DC source and resistors. Okay, this is resistors. Note down, this is resistors. Okay, so you will have to verify the Thevenin's theorem. So you will have apparatus like you'll be given the network. There will be a given circuit. You will need a constant DC source, DC source that will a source that will give you a constant direct current. Okay, and also you will need a variable direct current for the part 2, and then a multimeter. Okay, then a milliammeter, resistance box. All right, and if something else, something more than, etc. So what does the theorem says? As I already told you, a lot of this in detail will be covered up in your paper, but in practicals, let's just discuss this in brief. This theorem says that any linear bilateral network containing one or more sources connected to terminals A and B of a load can be replaced by a voltage source VTH in series with a resistance RTH, where VTH is the voltage across terminals AB when load is disconnected, and RTH is equivalent resistance across terminals A and B when load is removed, that is again disconnected, and all the sources replaced by their internal resistance. Fine, this is a long definition of what is Thevenin's theorem, but let us straight away go to the circuit diagram and understand what it means. So this is your circuit diagram, and this is some combination of resistors which is given to you, and this is the voltage that you'll get from the battery supply. Okay, some little voltage will be given, a direct source only, and in this loop you will have some current I1, and in this some current I2 because of this voltage source that is given to you, milliammeter, and the load resistors. Fine. Okay, so what the theorem says is that okay, before that, this is the kind of circuit it will be given to you. You can see this is R1, R1, R2 here, R2 here, R3, R3, and R4, R4. Okay, so, and of course these wires are kept so that we can do the remaining connections. So before that, just going back to what the theorem says, this is the circuit. Okay, this is the circuit which is given to you, and the theorem says that we can actually replace this complicated circuit here. You can see not so complicated, they are much more complicated than this, but for comfort purpose of us to understand this as we are doing it, we can replace this entire circuit. Okay, we can replace this entire circuit by simply a voltage source, an equivalent voltage source, and an equivalent resistance source. We call it Thevenin voltage, TH for Thevenins, and Thevenin resistance, giving you the current ITH. Okay, so you can see this milliammeter is as it is, the load resistance is as it is, just that all this entire circuit which was there can be replaced according to Thevenin's theorem by simply voltage VTH and RTH. Okay, so this is what we have to verify. So how do we verify it? What we will do is we will first take this circuit. Okay, we will first take this circuit and we will determine the current IA, okay, using the milliammeter. All right, after that we will construct this circuit using, for you must be knowing the Kirchhoff's voltage law and all. So we will solve this circuit and get VTH, RTH, and we will connect it this way and again find a current. Okay, so if Thevenin's theorem is true, then the current that you get using the circuit and the current that you get using the modified circuit, okay, the equivalent circuit it is called, should be almost same. Okay, very close to each other. The current should be very close to each other. Okay, so that is what the experiment is about. So before we start, let's determine what is RTH by using Kirchhoff's voltage law. I will not go in detail about Kirchhoff's voltage law and all. I'm sure you must be knowing it in your from your higher secondary. And even if not known, even the paper, it will be once again revisited in detail. Okay, when we are discussing the paper. Fine. So we have this circuit, okay, which is given to us, and the circuit that is given to us, which we are going to use in the experiment, this one is a 100 ohm here, 100 ohms, 100 ohms, and this is also 100 ohms, and on this one is 150 ohms. Okay, so the three are 100 ohm and this one is 150 ohms. Okay, fine. So this same thing I have taken in the circuit diagram here also. We have 100 ohms, 100 ohms, 100 ohms, and this is 150 ohms. Okay, so first let's find out the equivalent resistance RTH that we need. All right, so as you can see, the R1, if I take the circuit, first of all we need to disconnect the load. Okay, we disconnect the load for doing this calculation. There is nothing here on this side. So we just calculate the equivalent resistance using this. So you can see if I go by this circuit, then R1 and R2 are parallel to each other. This circuit R1, R2 is in series with R3. Okay, and this entire R1, R2, R3 is parallel to R4. Fine. So if you just recollect your basics, how do you write? I mean, R1 parallel to R2, how will you write? How will you write R1 parallel to R2? You will write 1 upon 100 plus 1 upon 100. Am I right? Okay, so what is 1 upon 100 plus 1 upon 100? It will be 2 upon 50, correct? Okay, so if I just say here R1 parallel to R2 will be simply 1 upon 50, correct? Because this will be 2 upon 100, so it will be 1 upon 50, correct? Now this is R1 upon R2, that is, it is some R prime, 1 upon R prime, it's parallel, right? So therefore this particular circuit R prime will be simply 50. Am I right? Okay, so this will be, this combination will be 50 ohms, right? Now 50 ohms plus, now R3 is in series, so that is also 100, so we get 150, right? This is 100, so we will get 150, correct? All right, so we have got 150. Let me erase all this now. So remember, this particular bracket that we have got is now 150. All right, so now this 150, this all three resistances, which is 150, is parallel to this R4, which is 150, right? So what do? We will write 1 upon 150 plus 1 upon 150, which is equal to 2 upon 150, which is equal to 1 upon 75, correct? Okay, now this is still not RTH. Okay, this is like 1 upon, say, R double prime, and therefore RTH will be simply 75 ohms, correct? Okay, right, simple. I think this you must have done in your schools also, how to find the resistance, but parallel and series. But then combination of these you must have done in your high secondaries when you were using Kirchhoff's the circuits theory, network theory, how you were solving. Okay, so this is a combination of resistors. You can see R1 plus R2 is parallel, so we get 1 upon 100 plus 1 upon 100 as 2 upon 100. 2 upon 100 is 1 upon 50. So therefore the resistance in parallel is 50, which is in series with R3 100, so it is 150. Now 150 is parallel to 150, that is R4 over here. So when we solve it, we get 1 upon 75. Therefore RTH, the equivalent Thevenin resistance, is 75 ohms. Okay, 75 ohms. So the RTH, I can replace it by 75 ohms. Okay, how to find VTH? Again, we can use Kirchhoff's voltage law for this circuit, circuit 1 over here. This circuit, if I use, okay, in this circuit the current is I1. Okay, the current is I1, and this voltage I have already measured using the multimeter. It's simple battery cell, which is actually supposed to be 1.5, but it is never 1.5 exact. It can be either little less than 1.5 or little more than 1.5. So what we do is we take a multimeter and we exactly find out what is the voltage. So I have found that this voltage is around 1.573. Okay, I had found it. All right, equal to, now let's solve this circuit. All right, the current is moving from negative to positive, so it's positive. So this is if I just consider only this circuit, then this 100 plus 100 is in series. Okay, if I ignore the remaining part of the circuit, only this circuit if I take into consideration, there 100 plus 100 is in series, so I get 200 I1. Okay, the voltage drop, there will be a voltage drop. This is 200 I1, correct? V is equal to IR. So IR, this is voltage that we have. So this is voltage 1.573 is equal to this voltage minus the voltage drop across this circuit. Okay, now this circuit will include only 100, which will be part of this circuit that we are discussing on this side, right? Okay, you must have used this in Kirchhoff's voltage law. So 1.53 is the voltage that is measured through multimeter. Okay, that is through multimeter, will be equal to 200 I1 minus 100 I2. 100 is this resistance R3. R1, R2 is already taken care in I1. Okay, so R2 is left with only this 100 ohms. Fine, so we get this equation 1. Now if you have to solve for the next equation, okay, if you have to solve for the next equation, in this circuit we do not have any potential that is equal to 0. Okay, so 0 is equal to negative of current I1, that is this 100 ohms, okay, plus 100 plus 100 plus 150, that is 350 ohms I2. Okay, the I2 current will deal with these 3 ohms over here, and from that side only 100 ohms. Is that fine? Okay, so these are the two equations, linear equations that we have, and you know how to solve linear equations simultaneously. Okay, maybe you can multiply equation 2 by 2, and so you will get negative 200, and this will be 700, and if you solve it, you will get I2. We are interested only in I2 because I2 is the one which is, this is the one which is in contact with this load and load that we are going to connect. Okay, so I2 is 2.62 into 10 raised to negative 3 amperes. Okay, therefore VTH will be R4, that is 150 into I2, and if you just do that, you will get 0.393 volts. Okay, so VTH will be equal to 0.393 volt. Okay, so if Thevenin's theorem is true, then whatever current I get using this circuit, I must get the same using this circuit. Okay, because I'm going to replace the entire this circuit that is given to us, by just simply a VTH, and RTH. Okay, we'll get Thevenin's resistance, Thevenin voltage, and create a equivalent circuit. So you can see such a big circuit just simply becomes a small one. Okay, and if Thevenin's theorem is correct, then it's a big advantage that you can make you can actually crunch the big circuits into small ones by just finding the equivalent voltages and resistances. Okay, so we now know that for this particular circuit that we have, VTH should be 0.393 and RTH should be 75 ohms. Fine, so now let us quickly go to the laboratory and perform the experiments quickly and see what the data is. Fine, so see you after the experiment. Alright students, so we can begin with our experiment now, and here we have all the components. This is this circuit that was shown in the explanation at the first part. Then this is the battery cell whose potential we have already found, and this is the milliammeter whose range is from 0 to 10, and this is the resistance box that we will be using. Fine. Alright, so let us just do the connections as we had shown, as we had discussed during the first part of this video. And here we have the same circuit given to you. As you can see, there's a resistance 1 here, 2, 3, 4, and these are 100, 100 and 100 ohms, and this is 150 ohms. If you want, you can even use the color codes, brown, black, brown for these three, and this is brown, green, brown for this one. So this is 100 ohms and this is 150 ohms. Fine, so we'll be using this circuit now for this experiment in the first part, and to prove the Thevenin's theorem, we will be then changing this with the equivalent of the resistance which we have already calculated. We have found that the Thevenin resistance as RTH is 75 ohms and VTH is 0.393 volts. Okay, so that we will have to replace this with the resistance box and a voltage source that we will do in the second part or third part of this experiment. Fine. Okay, so let's start the experiment. So as you know, we have this circuit that's connected to the battery, red to the red. Okay, and black will connect it to the black. So your left hand side of the circuit is ready. That's quite simple. Then we connect this end to the milliammeter. So we just have this crocodile clip here, which we just connected to this one. Fine. So that's done. Then the milliammeter goes to the resistance box. So let's connect it. Alright, and this is the resistance box, and the other end of the resistance box goes to the other end of the circuit. And as you see, moment I have done this connection, you can see there is some voltage current that is detected in the milliammeter. So let's take note of that current now for zero load. Right now, this the number of divisions between these two numbers, every two numbers that you have is 10. Therefore the smallest number that we have is 0.2. Therefore this reading is exactly here, so 0.2, 0.4, so 4.4. This reading will be 4.4. so let's take note of that, 4.4. Now let's take out 10 ohm resistance, 10 ohm resistance, and this is now decreased further to 4.2. so next reading is 4.2. Let's now take out 20 ohm resistance, so we can remove 20 from here and replace it with 10. So this has gone down to 3.8. Next is 30 ohms, so we take out this 10 ohms again. So now reading is now gone to 3.6. Next we have is 40 ohms, so take out 20 ohms from here, put it on this. So next reading we have is exactly 3.2. Okay, so this is like 2.2, 2.4, 2.6, 2.8, 3 and 3.2. Next we have is 50 ohms, so we can take out 50 ohms and replace all the other resistances. So we have 50 ohms, and the reading is 2.2, 2.4, 2.6, 2.8. Let's go for 60 ohms. Once again 2.4, 2.6, 2.6, yes, 2.6 and 2.6, yeah, correct, that's 2.6. Let's take out 70 ohms, and it is now 2.2, 2.4. For 80 ohms. So that's your 80 ohms. And we have 2.2, 2.4. Yeah, still on 2.4. Now we go for 90 ohms. So we just take off this 20 ohms from here, and that's it. It's now 2.2. And finally 100 ohms. You just take out this 10 ohms from here, so that's like 10, 20, 20, 50. 50 is 100, and we get slightly less than 2.2, so let's take it as 2.1. Fine, so with this we have come to an end of the first part of this experiment, where we have used this circuit that is given to you, and we have found the current that we have got. In the next part we are going to replace this. We are going to replace this with Thevenin's equivalent resistance, that is RTH, of 75 ohms. So we'll remove all this, and we'll have another resistance box like this, which will be kept fixed at 75 ohms, and we'll have a voltage source which will be kept at 0.393 volts. Okay, and we will see whether we are getting similar readings in the milliammeter or no. This will get totally replaced. Okay, so this will go now from here. This entire part will go, and it will be replaced by one resistance box over here, which will be your RTH, and another one voltage source, and we'll take the readings all over again. Fine. So let's take a small break, then we start with the part 2. Alright students, so now we are ready to do the second part of this experiment, where we are going to replace that circuit with an equivalent circuit. As you remember, in the while explaining you, I told you the RTH comes out to be 75 ohms. So this is going to be the RTH, which is going to be 75 ohms, and we calculated the Thevenin's voltage to be around 0.393. So this is the power voltage supply that I have, and we can see in the multimeter it's adjusted to 0.392 here. It's fine. Okay, so could not do that fine adjustment to 93, but this is 0.392. Fine. So we are ready to take the reading. So I will just remove this multimeter from here. Let's put this off and remove this multimeter, and we'll now connect the power supply. The power supply will be connected to the resistance that we are going to take. So maybe we can take a different wire. So we connect this to the RTH. Let's set RTH as we have already calculated. RTH is 75 ohms. So let me take out 75, 50, 20, 70 and 5. So the resistance box is now set to 75 ohms, and we have connected a voltage supply of 0.393 already. The other end of this goes to the milliamp meter. So it's connected. So this goes to the milliamp meter. The other part of the milliamp meter goes to the load resistance. So let's put back these resistances which we had removed in the first part and keep it to 0. And then at the end, the other part of the resistance comes back to the voltage supply, the negative part of the voltage supply. So just connect it. And yeah, the moment we do that, again we see we have this voltage. We have this current in the milliamp meter. So remember, we have the RTH to 75 ohms. We have set the power voltage supply to 0.393. Okay, so we see that the milliamp meter has shown current moment we just did these connections. Fine. All right. So let's start taking readings. The RTH is at 75. The load is at 0, and this is at 0.0393. So let's start taking our first reading. Now. Okay, so we start at 0 and we see our first reading is at 4.2, 4.4, 4.6. Okay, so we just note down the first reading, 4.6. Then we take off 10 ohm of resistance, and the reading is 4.2. Next is 20 ohms. Reading is 3.8. Let's take off another 10 ohms, that is 30, and the reading is 3.6. You can also follow me in the video. Next reading that we have to take is for 40 ohms. So let's take out another 20 and put this back in 10 ohms. So we get next reading is 3.2. That's correct. Next, let's take off another 10 ohms, that is 50 ohms. So reading is now, just calculate 2.2, 2.4, 2.6, 2.8. Next, let's take out another 10 ohms. So we are now to take 60 ohms. So let's take out 50 from here, put this 20 back, and another 10. So 50, 10 is 60 ohms, and we get our reading as 2.2, 2.4, 2.6. Another 10 ohms, 70 ohms reading. We have 2.4. Another 10, that is 80. It is 2.4. Yeah, exactly 2.4. Yeah. Next we have 90. Let's take off 90. And we have it at 2.2. And let's take out this 10 also. And this is 2. So with this we have come to an end of our experiment, and let's go back, do the calculations and see what results we get, and let's see whether the Thevenin's theorem is verified or not. Fine, so see you back again for doing the calculations in the next part of this video. Thank you. So welcome back. So you have seen the experiment. I'm sure it was very easy. I'm sure you must have found that very easy, correct? Okay. And what we got in the experiment are all these data. So let us just have a look at it. So we varied all the load resistances from almost 0 to 100. Okay. And the currents that we got, if you can see, except the first one, that is 0.44 and 4.4 and 4.6. Rest all the readings were same, and the last one 2.1 and 2. Okay, so for some reason maybe it was not that same, but if you see the current in the given circuit and the equivalent circuit were very close to each other, very close to each other. Okay, and if I calculate the theoretical calculation, so as you know, V is equal to IR, so I will be is equal to V upon R, right? So that means IL will be equal to VTH upon RTH plus RL, correct? Okay. So if I just do the theoretical calculation, then it is expected that, of course, when you do this calculation, you will get 5.2 into 10 raised to minus 3, but that will be answered in amperes. Okay, since we are milliamperes, we have written in the bracket milliamperes, so we can simply write 5.2, 4.6, 4.1 and so on. But you can see here it was expected by calculation 5.2, but we got 4.6, 4.4. 4.6 was expected, we got 4.2, 4.2. 4.1 was expected, we got 38, 3.8, 3.8, right, and so on. But this is expected because this is theoretical calculation, and when I do theoretical calculation, 100 ohms is 100 ohms, 150 ohms is 150 ohms, correct? But that will be not in real situation. A 100 ohm resistor may not be exactly 100 ohms. It could be little bit less than 100 ohms, correct? Right, because these are actual circuits that we are using. So actual circuits will have little bit resistances varying than what we actually write theoretically, right? So these calculations that we did using this formula and just varying RL every time. Okay, you can also do VTH. You remember what it is. We have done the calculation for VTH, and you remember what was the RTH value, right? So RTH was 75 ohms and VTH was 0.393. So if you just put different values of RL, you will get these calculated values. But still, the calculated values are very much in agreement of the experimental values that we got, correct? Experimentally, whatever values we are getting, it's very much close to that value. Okay, so which is a great thing, which is a very good data that we got, right? Okay, and about given circuit and equivalent circuit, they're almost same to each other. That is fantastic. Okay, and theoretical little variation, as I told you, because on paper it's very easy for us to write 100, 100, 100, 150 or any other resistance and just calculate. But in real life, when I say 100 ohm resistance, it might not be exactly 100 ohm resistance. There may be some variation in the 100 ohms, right? And therefore there will be some changes. The theoretical value may be little different from what you get exact value, right? So if you plot this data, of the load resistance versus inverse of 1 upon IL, then the graph would look something like this. And this is, don't worry about what has come here. This is computer generated graph. So what you have to only worry about is this intercept and slope. Okay, because the slope is your VTH. Okay, and intercept that is here, okay, is your RL. Okay, is your RL value. So what did we get? RL over here is negative because it is intercepting on the negative side, so it is 79. You can simply write 79 ohms. Okay, and slope is 370. that is VTH is 370, okay, which is equal to this is 370 amps, so amperes, so milliamps will be, okay, this is 370 volts, I'm sorry, this is 370 volts, so we are getting current in milliamps, so we're getting volts there, so actual answer will be 0.370, right? Okay, volts. Okay, and this is millivolts, that's what I mean. Okay, you have got this in millivolts because we are using current in milliamps, so you're getting volts in millivolts, but actual answer in volts would be 0.370, right? If I go, this is for the given circuit. If I go for equivalent circuit, here also very similar situation. This intercept, that is RTH, is 73 ohms, and the slope, that is here, slope is here, okay, is equal to the VTH is equal to 353 millivolts, which is equal to 0.53 volts. Okay, fine. You don't worry about all these other data that is generated by computer. You don't have to worry. On your graph, only these two, that is intercept slope and intercept slope, should be there. Nothing else is required. Okay, only these two values should come, one from the intercept, one should be slope. Okay, another very important thing about slope is don't use the data points to find your slope. Okay, find slope from any other point than the data point. Okay, take any point from the line that you draw, okay, instead of taking data point, because data point you have already found using the experiment, so no need to find data, no need to use the data point all over again. Get it? Okay, so don't do that. So you use any other point from the line to find your slope. Correct? So if I just tabulate the observations that I got, theoretically, when I calculated 75 ohms and 0.393 volts from the given circuit of the graph, I got 79.08 ohms, okay, 79 ohms rather, and 0.370 volts. And equivalent circuit is 73.33 ohms and 0.353 volts. Correct? Which is, if you can see, then you'll realize it is quite good data that you have got. We have done our experiment really well. Fine. And therefore we can simply write the result at the end, that the current in the given circuit and the equivalent circuit are nearly same and are within the experimental error limits. Hence Thevenin's theorem is verified. Okay, so you can write these things in your book, do the calculations all by yourself and check whether you are also getting the same answer. Plot these graphs using a lab book, okay, and how to enter this in the journal and all will be told to you. Okay, so don't worry about it. So I hope you have enjoyed the experiment, so we'll stop with this. Okay, thank you.